Okay, hey, welcome back. This is 9.3. Probably should have noted that here. Integral and P-series, and the integral test is the first thing we want to look at. And the integral test is pretty simple. Basically, you're looking at the series a sub n from I guess n equals 1 to infinity, and then comparing that to the behavior of the integral from 1 to n, or 1 to infinity rather, so it's an improper integral of f of x dx. Okay, you know how to do this from chapter 8.8. So basically, if you take the, so if you have something like the sum of 1 all over x plus 1, and of course we don't use x's in our summations. If you have the sum of 1 over n plus 1 from n equals 1 to infinity, you can determine if that converges or diverges by just looking at the integral from 1 to infinity of 1 over x plus 1. So you just replace the n with x and then evaluate that integral. If this integral diverges, then the series diverges. If the integral converges, then the series converges. You can't always do this. There are some initial considerations, but in this case we can. So let's, for kicks, just figure out what we got here. Limit as n goes to infinity of the sum from 1 to n of 1 over x plus 1 dx. You do u sub on that guy, and you'll end up with just du is dx, and then you'll get the ln of u. Back sub, you end up with the ln of x plus 1 from 1 to n. We usually use b, I know, but for whatever reason I just used n. So anyways, that'll be the limit of the ln of n plus 1 minus the ln of 2 as n goes to infinity. And that ln of n plus 1 will go to infinity minus some constant L. So that'll be infinity, and it'll be divergent, which then says that this guy is also divergent. Okay, so it's not the case where it'll tell you what it sums up to. So in the previous section, you know, we had the geometric series, we had the telescoping. In those cases, we could actually figure out kind of the limit of the partial sums. Okay, so we can know that. Here, that's not going to be the case. Even if you can figure out the integral, that answer will not necessarily be the same as the sum of the series. Okay? And that's generally the case. Generally, you won't be able to find the exact sum. You'll have to do some sort of approximation. These geometric and telescoping are kind of the only instances where we'll be able to figure out the sums exactly, because we'll be able to figure out this S sub n formula. And then take the limit. Okay, so that's the idea in a nutshell. The P-series turn out to be provable via the integral test, and we kind of lump those together and approach those like we approach the geometric series. So you'll be able to kind of look at them and know, based off of one element, whether they're divergent or convergent. Okay. Okay, so first we want to look at the integral test. We kind of want to prove it as well. Integral test, and so what is the integral test officially? There are some suppositions you need to hold. So we're comparing this again. It's comparing this series to this function, this integral of a function, an improper integral, and basically, all you're doing is rewriting a sub n as f of x. So in the definition, you're going to hear me talk about f of x, but really you're kind of just talking about this a sub n at first. Okay, so first off, we need a sub n, or in other words, f of n, to be positive, continuous, and decreasing, or rather here, f of x, right? So if f of x is continuous, so we could take its integral. Positive and decreasing. Okay. For eventually, for some x value eventually, so it will say for x greater than or equal to, some number a, some positive number a. Okay, so we'll say a is greater than or equal to 0. I think the book uses 1, but it's an eventual criteria. So if it holds eventually, that's good enough. Okay, and also noting, you know, a sub n is kind of the mirror of f of x. So a sub n is equal to f of n. If all that holds, then the series from I equals 1 to, I'm using a different letter now, so n equals 1 to infinity of a sub n, that and the integral from 1 to infinity of f of x dx will have the same behavior. In other words, they both diverge or they both converge. Okay, to kind of prove this to you, and this isn't an official nice proof, it's just kind of a sketch of a proof. You can read the proof in all of its glory in the book. But in order to prove this to you, what we're going to do is build a compound inequality and then sort of note the two cases. So one case where the improper integral converges and one case where the improper integral diverges. Okay, so we begin by kind of drawing a picture. So here we have a picture of f of x over the interval from 1 to n. The function is continuous, positive, and decreasing. Okay. I'm going to first put some rectangles above, so it's called below. It's called inscribed rectangles and then circumscribed. So I need to put the use the right-hand endpoints to pull this off. And then on and on, all the way up to n. And this other endpoint would be n minus 1. Okay, so the area underneath this curve, the rectangles represent individual terms from the series. Okay, so this would be a sub 2 all the way up to a sub n. Or actually, this would be sort of a sub 2, and then, well, I'm not going to overthink it. We'll just make it a sub 1. I'm not even going to label that guy. Okay. So a sub 1 in this case is going to be, given that this is a function f of x, a sub 1 is what? Well, the area of that first rectangle, and I can use this coordinate 2 comma f of 2. The area of that rectangle will be the height of the rectangle, which is f of 2, times the base. And the base, the way we've set it up here, is 1. Okay? So that will be equal to f of 2. But we recall that f of n is equal to a sub n. Okay, so you could also rewrite that as a sub 2. And then a sub 2 is f of, this point here is 3 comma f of 3. So a sub 2 is going to be f of 3 times the base. 3 minus 2 is 1. So that'll just be equal to f of 3. And of course, f of 3 is just a sub 3. Okay. So what you have with these rectangles, the areas of these rectangles, is basically a partial sum of the series. So you have a sub 2 plus a sub 3 plus dot 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 plus a sub n or whatever. And what is that? Well, that's basically the it's sort of S sub n, right? So if you remember what is S sub n is kind of that, but not really. S sub n is a sum from I equals 1 to n of a sub I, which would have been a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n. So this thing is S sub n, but not really. It's missing part. It's missing a sub 1. So you could, if you want to, you could rewrite it as S sub n minus a sub 1, whatever the first term of the series is. Okay. So there's that thing. this is less than or equal to then the actual area underneath the curve from 1 to n. And you would find that area by just integrating. So the integral from 1 to n of f of x dx. Okay? And then we'll compare that to circumscribed rectangles. So you can go through the same process now of putting all the rectangles on the top. Let's make sure I'm actually recording. Yeah. Okay. So we'll go through this again, and you just get a different portion of the partial sum, right? So if you have our f of x function, the same function, and then 1, 2, 3, you don't need a lot of them, and then all the way up to n minus 1, and then n. This time we're going to use the left-hand endpoints, and you see the rectangles will go out above the curve. So the area of these rectangles, when you add them up, is going to be greater than the integral. Okay. Okay. So what is that thing? The area of the first rectangle, if you're using that point here, 1 comma f of 1. The area of that first rectangle is going to be f of 1 times the length of the base, which is 1. And of course, that's just equal to f of 1, which is a sub 1. Right? And then, you know, so on and so forth. A sub 2, the area of the second rectangle, will equal little a sub 2. And then let's call this one a sub n minus 1. A sub n minus 1 will equal little a sub n minus 1. Okay? So you can always kind of think of area as a summation where you're summing up a bunch of numbers, but each one of those numbers is, you know, you're summing up like 1 plus 2 plus 3. You could think of that as areas of rectangles where the height is, you know, 1, 2, 3, but then the base is 1. Okay, so you kind of, it's kind of like cheating a little bit, but anyways, you could take any sum and revision it as a sum of areas. Okay. Okay, so anyways, there's that. So what is this thing kind of in terms of our partial sums? Well, this thing goes from A1, A2, A3, A4, like over here. So here's our actual S sub n formula. What is this thing that we're playing around with? This thing is everything except A sub n. Okay, so we could write S sub n minus A sub n, but you could also think of it as S sub n minus 1. Okay, so S sub n minus 1 is just going to be the partial sum from I equals 1 to n minus 1, okay, of A sub I. So it's basically just a sub 1 plus a sub 2 plus dot 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 plus a sub n minus 1. You're missing the a sub n. Okay. Okay. So we've built this inequality. Now what? Well, the test kind of hinges on your ability to determine whether or not the sum is divergent or convergent. So again, if you build your integral and you find the integral is divergent, it forces the summation, or the series rather, to be divergent. If you do the integral and it turns out to be convergent, it'll force the series to be convergent. So the forcing is going to come from this inequality here. So what did I say? Let's presume that the series, or rather, let's presume that this improper integral is convergent. So suppose the integral from 1 to then infinity of f of x dx is convergent. Okay. In that case, it will have S sub n kind of bounded above. Okay. In that case, S sub n minus a sub 1 will be less than or equal to some number. So you can say, you know, if this thing is convergent, we know it equals something. I don't know what it is, but let's just call it, let's see what I called it in my notes, L. Okay. Okay, this is important because we just had in chapter, I think it was 9.1, the monotonic bounded convergence theorem, which says if you have a series such that its terms are increasing and it's bounded above, it's convergent. So notice, or we note that because the terms, let's just say the terms a sub I are increasing, or rather they're not increasing, right? They're decreasing, but the point is they're positive, right? So because the terms are greater than 0, S sub n will be increasing. Okay, so one of our conditions for this to work was that f has to be continuous positive and decrease, but that positive part is what's helping us right now. If f of x is positive, then a sub n will be positive because f of x is positive for all x greater than or equal to this a. So a sub n must be also positive. Maybe I shouldn't use an a there. I should have just used like b or something. But all the terms would be positive. So what is S sub n? Well, S sub n is just a sum of a bunch of things. And so if you went from S sub n to S sub n plus 1, you know, S sub n plus 1 is S sub n plus A sub n plus 1. You know A sub n is positive. So what happens is that S sub n is increasing, going from one to the next. If you're adding something positive in, S sub n will be increasing. So that's what I'm saying here. We know because the terms of A sub I are greater than 0, S sub n will be increasing. Also then, S sub n is bounded above. And you can see clearly S sub n minus A sub 1 is less than or equal to L. And then you could completely solve for S sub n, so to speak. And S sub n will be bounded by L plus the first term of the series. Okay. So if it's increasing and bounded above, it's convergent by the monotonic convergence theorem. Okay. So hence, the sequence of partial sums is increasing and bounded above, and thus convergent. So if the improper integral converges, it forces the series to converge. Okay, so that's one version. So let's suppose the other way, right? Suppose now the series from 1 to infinity of f of x dx diverges. Okay. We then note that the integral from 1 to infinity of, or just plain old 1 to n, of f of x dx will be less than or equal to s sub n minus 1 as n gets pushed to infinity, which is what we do for our improper integrals. So we note this inequality. As n goes to infinity, it forces the partial sum to also go to infinity. In other words, they'll both diverge. So just one other note that S sub n minus 1 and S sub n will have the same behavior. If you're looking at S sub n minus 1, it's just basically the sum of the first n minus 1 terms. So if you were to increment that by 1, you would just be at S sub n. And then the point being that they both have kind of the same behavior. Okay? It's not going to affect anything by just removing one term and then taking the limit of that thing. Okay, so hopefully that you can stomach that that part of the proof. Okay. So it's basically as this thing gets really, really big, it's going to force the sequence of partial sums to get really, really big. And if the sequence of partial sums goes to infinity, the series is divergent. And I'm saying that this S sub n minus 1, don't worry about that. You can treat it just like it's S sub n. Okay. Right. So hence both will diverge. Okay. So let's go ahead and take a look at some of these examples. So first one, sum from n equals 1 to infinity of 2 all over 3n plus 5. Okay. So it's not geometric. It's not like you can't do like a partial fractions on it. If you do the nth term test for divergence, you're looking at that. That'll go to 0, which tells you nothing. So noting, just being a little more careful about how we present our work, noting the nth term test for divergence. The limit of that thing goes to 0, hence there's no conclusion. Okay. The only conclusion you can ever really make there is if it doesn't go to 0. So if that does not go to 0, it's automatically divergent, and you could stop. Otherwise, you're kind of out of luck. Okay, so we try the integral test. So we try the integral test. And sadly, there's 3 things you got to check for the integral test, right? You got to check. So we got to consider first off the function f of x equals 2 all over 3x plus 5. And we're going to work on the same interval that the series is suggesting. So we're going to go from 1 to infinity. Okay? So on the interval from 1 to infinity. Sorry, I didn't go back to white. Okay, so first we have to show that it's continuous. If you remember your work in Calc 1, basically rational functions are continuous everywhere except where their denominators are equal to 0. Note our denominator, 3x plus 5, does not equal 0 in this interval, right? So it only equals 0 when 3x is negative 5. In other words, when x is negative 5/3. So it only has a discontinuity there. Is the only discontinuity. Hence, it is continuous on our interval. Okay. Secondly, then, is it positive? So note, x was originally supposed to be greater than or equal to 1. If you multiply both sides by 3x, that's greater than or equal to 3. And then if you add 5 to both sides, you get 3x plus 5 is greater than or equal to 8, which of course is greater than 0. Hence, for x greater than or equal to 1, what was the numerator? 2. 2 all over 3x plus 5 will be greater than 0. Okay, because it's always going to be a positive divided by a positive, which is positive. Please note 0 is neither positive nor negative. Okay, 0 is even, but it's not positive nor negative. So if you have a positive divided by a positive, it will always be greater than 0. Okay? So yes, it is positive. Okay. Thirdly, then, we need it to be decreasing. again on this interval or eventually decreasing somewhere. So in this case, you usually just can go to the derivative. Okay? I gave you monotonicity tests in section, I think it was 9.1, when we were talking about the monotonic convergence theorem. But here, I think it's better just to use the derivative. So f of x is equal to 2 times 3x plus 5 to the negative first power. F prime of x will equal negative 2 times 3x plus 5 to the negative 2 power. In other words, that's equal to negative 2 all over 3x plus 5 squared. Okay. And then I just need to compare that to 0, right? In this case, 3x plus 5 squared, anything squared, so long as it's not 0, will be positive. We already showed that 3x plus 5 is positive. So squaring it, it'll still be positive, and then the numerator is negative. A negative divided by a positive is negative. All negative numbers are less than 0, so we can conclude the derivative is less than 0. Hence, it's decreasing on that interval. It's actually decreasing, yeah, on that interval. It's decreasing everywhere, except where it has its discontinuity. Okay. So, but anyways, long story short, it's decreasing. Okay. Usually on a test, I won't worry so much about the first two. So I won't worry about you showing it's continuous or proving it's positive. That positive one, that proof for being positive is kind of weird, and people aren't used to doing that. But I expect anybody to be able to do the decreasing test, so you'd have to take the derivative and show that it's negative. Okay, you don't necessarily need to go through my argument, okay, it's a negative divided by a positive and all that jazz, but I would expect to see the derivative, and then I would expect to see you compare that to 0. Okay. And if you have this inequality, you can make your conclusion, hence it's decreasing. Okay, hopefully that's clear. So I won't be doing, I don't need you to show it's continuous and positive, just show it's decreasing. Okay, so once you've shown all of that material, then you can go ahead and apply the integral test. Okay, okay, so let's try it. So note the improper integral. Integral of 2 all over 3x plus 5 from 1 to infinity of dx is, and here we need well, you can drop the integral symbol and take a limit as we approach it. Going from 1 to b now, and I have 2 times, so this will be a natural logs type, so we can kind of leave it as is. 2 all over 3x plus 5 dx. You'd end up doing a u sub, so your u sub would be 3x plus 5, du would be 3 dx, so dx would be du over 3. So you'd have a 1/3 constant out in front, and then you'd have 2 over u, so you could pull out a 2. The integral of 1 over u would be ln of u, and then back subbing you get ln of the absolute value of 3x plus 5. Okay. And then we're going from 1 to b. Okay. So this will equal the limit as b goes to infinity of 2/3 ln of the absolute value of 3b plus 5 minus 2/3 ln absolute value of 3 plus 5, which is just 8. Okay. And then as b goes to infinity, the natural log function, of course, also goes to infinity, just very, very slowly. So this will be infinity minus some constant, which will equal infinity, which means it diverges, and hence the series diverges. Okay. Okay, let's do another one. So this one is a little weirder because of the way it's decreasing. So example, we have the sum from n equals 1 to infinity of n e to the negative n over 2. Okay, okay, so again, we're considering sort of its mirror function, f of x equals x e to the negative x over 2. hopefully on the interval 1 to infinity, but kind of the point of this problem is to show that you could just push that, that number 1 out, okay, if you need to. Okay, so first we need to show it's continuous on this interval. It's actually continuous everywhere because we note y1 equals x is continuous, and y2 equals e to the negative x over 2 is continuous. Hence, the product of continuous functions is also continuous. And this is a chapter, this is a Calc 1 fact. So if you missed out on that in Calc 1, it's in the book, it's in the section on in limits, where they kind of connect limits to continuity. Okay. Actually, there's a section on continuity, isn't there? So basically, if the limit of f of x as x approaches c equals f of c, then the function is continuous, okay, at c. And in general, if you could take the limit via a substitution, it's continuous. Okay, so anyways, hence the product of continuous functions, or at least that's what we're doing. F of x is the product. I should try to write in good English here. We note f of x is the product of continuous functions and thus continuous. And it is everywhere continuous, not just on the interval. Okay, so secondly then, is it positive? We note then y1 again equals x is positive, basically from 1 to infinity. And e to the negative x is positive everywhere. We know that f of x is the product of these. The product of positive functions, and therefore it's positive. Positive times a positive is positive, right? So it's the product of positive functions and the product, and this product, it will be positive. So what the heck did I write? We know y1 is positive from 1 to infinity, and y2 is positive everywhere. We know f of x is the product of positive functions, and thus will be positive. Okay. Then thirdly, we got to show it's decreasing on this interval, hopefully. So let's get the derivative. F of x is x e to the negative x over 2. Okay. F prime of x will be, via the product rule, x e to the negative x over 2 times negative 1/2, and then plus the derivative of x is just 1, so you'll have e to the negative x over 2. We want to set this equal to 0 to kind of get the critical numbers. So we have 0 equals negative 1/2. You could factor out e to, let's factor out e to the negative x over 2. So you get negative 1/2 x plus 1. E to the negative x will never equal 0, so we just plop negative 1/2 x plus 1 equal to 0 and solve that. That will give you negative 1/2 x equals negative 1, so x is equal to 2. So on our interval from 1 to infinity, there's an issue because it's not necessarily always increasing, right, or decreasing. So we could do some test values, try x equals 3/2 here. If you plug 3/2 into the derivative here, the e to the negative x over 2 part is always positive, but on the inside here, 3/2 times -1/2 is -3/4 plus 1, that's positive. And then out here, let's try x is 5. -1/2 times 5 is -5/2 plus 1 is negative. So it really doesn't begin decreasing until after 2. So hence, it only starts decreasing after x equals 2. So what we do is just push out that number from 1 to 2. Okay? It's still continuous on that interval. X and either negative x over 2 are continuous everywhere. The product of continuous functions is continuous. Both functions are positive from 1 to infinity, so they're definitely going to be positive from 2 to infinity. So all we need to do is consider it from 2 to infinity. So hence, we just consider that interval, and that'll be fine. X on 2 to infinity. Okay. Right. So let's go ahead and figure out that integral then. So we take a look at the improper integral from 2 to infinity of x e to the negative x over 2 dx. Again, we can rewrite it as a limit as b goes to infinity of the integral from 2 to b of x e to the negative x over 2. We need to do by parts on this thing. Okay. So our u and our dv. Leah says u is x, and then I have negative x over 2 dx, and then du will be just dx, and then of course v negative 2e to negative x over 2, and then we want to rewrite this as a limit as b goes to infinity of negative 2e to the negative x over 2 minus, it'll become plus the integral of 2 times e to the negative x over 2 dx. Okay. And I have to remind myself to evaluate. This will be the limit as b goes to infinity of negative 2e to negative x over 2 plus, or rather, in this case, it'll be minus, right? There'll be an extra constant of 2, so this will become 4e to the negative x over 2, evaluated from 1 to b, or from 2 to b. So that will equal the limit as b goes to infinity of negative 2e to the negative b over 2 minus 4e to the negative b over 2 minus, then, well, I guess you could combine those, right? I wonder why I didn't combine those in my notes. Oh, I lost an x. That's why I didn't do that. So there's an x here. There's an x here. I apologize. And then there'll be, this will be negative 2b. So I'm going from 2 to b. So negative 2b e to the negative b over 2 minus 4e to the negative b over 2 minus, plugging in 2, I get negative 2 times 2e to the negative 2 over 2 is negative 1 minus 4e to the negative 2 over 2, which is minus 1. And then I can figure out these limits. So this character here, let's say it's going to probably go to 0, right? Because that negative exponent will drop the e to the denominator, and then it'll get huge on us. This guy here, see, you're going to have to do a L'Hopital's, right? So this will be the limit. Let's just look at the b all over e to the b over 2. So notice it's negative, but if you drop it to the denominator, it will be positive as b goes to infinity. This is infinity over infinity, so you do a L'Hopital's, limit as b goes to infinity of 1 all over e to the b all over 2 times 1/2, and then that'll go to 0. So this part will also go to 0, just based off that little tidbit of information. So at the end of the day, then you just are left with these constants. So we have, looks like negative 8e to the negative 1, but negative negative becomes positive 8e to the negative 1. Hence it's convergent, so hence the original series converges. Okay. You can't say it converges to that number though, so just be aware of that. This number will be different than the actual sum, and it has to do with the way, you know, the series is basically the rectangles, and the integral is basically the area underneath the curve. So there's going to be, you can't expect them to be the same answer. Okay, they're just geometrically different. Intuitively geometrically different. It may be the case that you could find some that are the same, but I don't know. I've not studied it in that depth. Okay, so anyways, section 2 then is on the p-series and the harmonic series. And these guys are have the form, the sum of 1 all over n to the pth power from n equals 1 to infinity. Okay, so we claim that this thing is going to be convergent if p is greater than 1, and then divergent if p is greater than 0 but less than or equal to 1. Okay. So all you technically have to do is look at the p-value. So for example, number 30, or it used to be number 30, let's just put it as an example. So for example, the series from n equals 1 to infinity of 1 over root n. You know, what's the p-value? This kind of becomes the game. This will be 1 all over n to the 1/2 power. So the p-value, is it even going to be convergent? You know, the p-value is in between 0 and 1/2, so no, this one's divergent. So the p-value equals 1/2, which is less than or equal to 1, hence it's divergent. It's a divergent p-series. Okay. So maybe look at one or two more where they try to trick you a little bit. So another example, this time they just give it to you as a sum, 1 plus 1 over 2 root 2 plus 1 over 3 root 3 plus dot dot dot. Rewriting it as a sum from I equals, or we're using n's, from n equals 1 to infinity, it's 1 all over n root n, right? And then you could rewrite that, so that will be the series from n equals 1 to infinity if you just add the exponents. So it's really n to the first power times n to the 1/2 power. So to be 1 all over n to the 2/2 plus 1/2, which will be 3/2, n to the 3/2. So here this is this has a p-value equal to 3/2, which is greater than 1. Hence, it's convergent. Okay, so that's all that rigmarole. In general, we can prove that this thing is, you know, where it diverges and where it converges. The kind of frontier between convergent and divergent, where p equals 1, is called the harmonic series. So note the series of 1 all over n from n equals 1 to infinity is called the harmonic series. It's a very special series, and this guy is divergent. Okay. Harmonic series, that's where p equals 1. Okay, so the point is you can use the integral test in order to prove the sort of above criteria for convergence and divergence. Okay, so I guess I call this a proof. I don't know. I don't really want to call it that, but okay. So proof. We can. Okay. So what are we dealing with? The integral of 1 all over n to the pth power dx, basically. So let's presume it is positive, continuous and decreasing, and so we want to know. Yeah, let's not even call this a proof. Okay, so I'll just say we want to know for what p-values the series 1 all over n to the p converges or diverges. Okay, so first we're going to use the integral test. And we're going to presume it's continuous, positive, and decreasing on our interval. Okay. Okay. So to use the integral test, we kind of have to split this into two types of integrals. The first type will presume that p is not equal to 1. Because if p is equal to 1, you got to use the natural log. Okay. So when p is not equal to 1, this thing, when we integrate it, and we'll take, replace the bad limit with a b, as b goes to infinity, of x to the negative p dx. What do we have then? The limit as b goes to infinity of the integral of x to the negative p is x to the negative p plus 1, but let me rewrite that as 1 minus p, all over 1 minus p. And then we need to evaluate this thing from 1 to b. Okay, so that'll equal the limit as b goes to infinity of b to the 1 minus p all over 1 minus p minus 1 to the 1 minus p. 1 to any power is just 1, so I'll just have 1 all over 1 minus p. And then the limit of this thing is completely dependent on that first term, and in particular the p-value that's involved in that first term. Okay. So we'll kind of extract this guy and take a closer look at it. So the limit as b goes to infinity of b to the 1 minus p all over 1 minus p. Okay, so I claim there's two cases here. One case is when 1 minus p is less than 0. Okay, when that happens, that numerator is going to drop to the denominator, and you're going to get L over infinity form, which will equal 0. In other words, in this case, it'll be convergent. So p will be greater than 1, and it'll converge. In the other case, that's when 1 minus p is greater than 0. And in those cases, it'll just shoot off to infinity, right? So in this case, p is actually less than 1, and it'll diverge. Okay, so far, what do we have? And we're assuming p is greater than 0. If p is, so this tells us so far that if p is less than 1, it's divergent. And then if p is greater than 1, it's convergent. Okay. So the last case we need to kind of look at is what happens when p is actually equal to 1. So when p is equal to 1, it kind of changes the integral. So we need to go back to our integral and evaluate this thing from 1 to infinity. This will equal the ln of the, it's the limit as b goes to infinity of the summation, the integral from 1 to b of 1 over x dx, and then that will equal the limit as b goes to infinity of the natural log of x evaluated from 1 to b, and then that will equal the limit as b goes to infinity of the natural log of b minus the natural log of 1, which will just be 0. So it's completely dependent on how the natural log behaves as b goes to infinity, and of course that will just be infinity, okay, which implies it's divergent in this case. Okay. So going back to our statements here, and then sort of channeling this into it, when P is less than or equal to 1, it's actually divergent. Okay, and that'll include then the harmonic series. So the harmonic series, the way that thing kind of plays out, it's divergent, but it's extremely slowly divergent. Okay, and let's go to Wolfram. So the deal is, it's almost like if you added up one part of the harmonic series every second, it would take to the end of the universe just to add up enough terms to get you to like 1,000. It's slowly. It's just slow as molasses. Okay, so 1 over, let's look at the sum, 1 over n. From n equals 1 to 100. Okay, when you sum from 1 to 100 with the divergent harmonic series, it only adds up to 5 from 1 to 100. So let's go to that. It's only up to 25. This thing just diverges slowly. And it's incredible that it's actually divergent. You would expect it to be convergent because of the rate at which it sums up. It's only at 69 right now. Okay, so it's just unbelievable how long it takes this thing to reach a certain number. But any number you produce, this thing will eventually exceed it. Okay, it'll just keep growing and growing and growing and growing indefinitely. It's never going to converge to anything, right? It's still at 92 after. So literally, you could probably sum this to what are the number of seconds in the universe? Number of seconds. Let's say the universe should exist. Now what are the number of atoms in the universe? So if you turned every atom into I don't know, 10 to the 78ths, 10. So if we turned every atom into a number and added them all up, 10 to the, let's say 10 to the 82. Let's just be 10 to the 82. You'd only get up to 189. The number, let's go back to the number of seconds. So if somebody started adding them up 1 a second from the beginning of the universe, number of seconds since the Big Bang, since the beginning of the universe. That means 10 to the 21. Apparently 10 to the 21 seconds. There's more atoms in the universe than there are seconds. So there's no way. This won't even get up to 200. Yeah, it's only at 48. So, okay, so mind-blowing stuff. We'll stop the lecture there, and I'll see you next time.